Hello everyone, I will be presenting to you my FYP topic on DNN FES and Fole, which is an objective loss estimator that is used to integrate deep neural network into fuzzy systems. Here is the overall order in which the topics will be covered. First, we will be going through the basic concepts that are required to understand the research. Then we will look at the DNN FES model architecture. Next is the Fole learning mechanism, which is the novel learning mechanism devised in the research work, apart from the DNN FES. We will compare the performance of the DNN FES with the existing state-of-the-art model. Lastly, we will look at the application side of the research work, which is the stock market prediction. So first, let's understand the basics. A fuzzy set differs from a traditional understanding of a set. Instead of having a hard threshold to categorize if an element belongs to the set or not, fuzzy set instead provides a membership of how much an element could possibly be belonging to the set. This membership is given by a membership grade and described using a possibility distribution. Usually, a fuzzy set is denoted by a linguistic variable, such as short, long. Fuzzy logic uses the fuzzy sets in order to derive an implication. It consists of rules that are of the form if, then, as should. Consider the rules. If it rains, I'll bring an umbrella. If the antecedent is, if it is not raining, the consequent will be, I will not bring an umbrella. Fuzzy system combines both the above components to sort of create a model that is able to perform a predictive task. For example, given the quality of service and food, predict the tips that would be received by the waiter. Fuzzy system primarily uses a rule set stored in the knowledge base. The knowledge base also stores the fuzzy membership function that is used to calculate the membership grade. There are primarily two types of fuzzy system, Mamdani and TSK. Mamdani systems are approximate reasoning method that provides if-then rule. The consequent of a Mamdani rule base consists of fuzzy set. Hence, there is an imperative need to convert the output fuzzy set into crisp value using a defuzzification method. They are highly interpretable. TSK are more accurate system. The consequent of the rules are linear combination of input values in the real domain. At the end, both the system requires the weighted average of all the rules that are triggered to finally produce the combined output. Neural networks are human brain inspired intricate structure. They can approximate any function given a sufficient amount of data representing the function. Many research models have been proposed to solve specific tasks, such as CNN for dealing with image data and RNN for dealing with temporal information, such as time series. The weights and biases, which are the learnable parameters of the model, are updated during the training phase, using the gradient descent method. The equation of the learning is shown in the slides. The alpha is the learning rate, and the weights are updated in the negative direction of the loss, which is being tried to minimize. This slide provides an overview of the LSTM cell, which have been extensively used in the project. It is one of the key components that stores temporal information explicitly in the form of cell state. The amount of information that flows through each time step is controlled by three gates: input, output, and forget gate. The input controls how much information from the current timestamp needs to be stored into the LSTM cell. The forget gate controls how much of the previous temporal information needs to be stored. The output gate controls the information that is finally projected outside of the LSTM cell. The current NeuroFuzz system adapts the structure of the neural network. It does not use the gradient descent algorithm to update the rule base. It uses the training samples to create the rule, making the system quite fragile to new data point. It also uses a single t-norm as an implication method for providing the membership grade of the output fuzzy set in the consequent. An example of the NeuroFuzzy architecture is shown on the right, called POP FNN. For more detail on this topic, please review the background information section of the research paper provided. Let's now focus on the main research topic, which is DNN FES, or Deep Neural Network Fuzzy Embedded System. DNN FES is a deep neural network embedded fuzzy system. It combines the accuracy that is observed from neural network architecture as well as the interpretability that comes from the fuzzy rule. The advantages or salient features of the model architecture is that the fuzzification algorithm can be of any type. Secondly, the deep neural network can be of any type. Thirdly, the rule tagging system that runs parallel to the neural network provides the interpretability of the black box nature of the neural network. In the forward pass, porting the term for neural network field consists of three steps. First step is to convert the real values into fuzzy inputs using a fuzzification method of choice, such as DIC, CLIP, or MLVK. Second step is to make the implication by passing the values to the neural network and a fuzzy rule base. The rule base sheds the interpretation of the calculation taking place in the neural network. Third step is to aggregate the output grade from each fuzzy label and provide a declassification using the center of area method. The formula is shown on the slides. The neural network used can vary with choice. In the current research work, LSTM and simple MLP is used to demonstrate this. The input to the neural network is the falsified values obtained from fuzzification method. The output of the neural network model is membership grade for each of the output fuzzy set. The advantage of using a generalized modus ponens implication method is captured by the neural network, replacing the standard T-norm, resulting in better generalization. The parallel fuzzy system provides the interpretability of the black box model. The rules are derived by identifying the input nodes that are triggered having the highest membership grade in the input fuzzy attribute. The corresponding weights of these rules are updated using the Heb learning method. In short, it states that the more frequently triggered rules have a higher weightage. Heb learning weight is monotonic in nature. They include the forgetting nature of humans. A forgetting factor is multiplied in every time instance of the learning phase. Now let's come to the exciting part of the research, Fole, a fuzzy objective loss estimator. There are primarily two types of losses, MSE and cross-entropy loss. MSE loss is used in a regression setting where the output is a numerical value, while the cross-entropy loss is used in a classification setting where the output is a class. The MSE loss function can be incorporated in the last layer of the model architecture to calculate the disparity between the actual and the predicted values from the fuzzification. The cross-entropy loss function can be incorporated at the membership output layer. In this case, the neural network will be learning the possibility distribution of the output variable. We first tried using the MSE loss function to train our model. We in fact observed good results in terms of low RMSE and high R-score. However, if we look closely at the rules that are generated, you can notice that the rules are inadmissible. Consider the rules that are generated next to the blue ribbon. In order to get the predicted values as close to the actual value, the model uses the largest and the smallest fuzzy sets and ignores any intermediate sets. In order to tackle this issue, we used the cross-entropy loss. In this, we were able to get admissible rules. However, the model performance deteriorated. So intuitively, the MSE controls the performance of the model architecture, while the cross-entropy controls the interpretability of the rules. FE works exactly by combining both these losses. Fole uses both the cross-entropy and the MSE loss. The MSE loss can vary to a large extent depending upon the dataset, while the cross-entropy loss can be quite low since it is the negative log likelihood of the value. In order to balance these values, an additional term is multiplied with the cross-entropy term. This is calculated using the formula shown on the slides. Here phi and lambda are hyperparameter that needs to be set depending on the dataset. The idea is inspired from the communication, where the disparity between the two information sources is measured by the number of bits that are required more. At the end, both the errors are of the same magnitude. The end results of using Fole produces better performing models with interpretable rules. If you look at the rules next to the blue ribbon now, you may notice that the rules are admissible and the center of the fuzzy set that is nearest to the output value is triggered. Let's look at the benchmarking tests. The first benchmarking test is performed on the Nakanishi dataset, which consists of 3 subsets. For more information regarding the dataset, please refer to the thesis paper. Looking at the table on the right, you can notice that for the first dataset, DNA and FES comes second after Safin. For the chemical plant and the stock market dataset, the model comes first, beating the current state-of-the-art models which have been published in top journals such as IEEE. A summary of the effectiveness of the Fole is provided on the left. Overall, it is able to improve upon the RMSE by reducing it and increasing the R-score as compared to using a standard MSE loss. The traffic dataset is unique in terms of the nature of its collection. It is a real dataset that contains the traffic volume that has been captured along the PIE road as shown in the image. The lane 1, 2 and 3 shown in the image are the main point of focus along which the traffic volume will be predicted. The table on the right shows that DNN FES model performs better than any of the current models. We do not mention the RMSE because of the current dataset. the usual metric of comparison and literature used is R-score. The table on the left shows the efficacy of using Fole over the standard loss estimator. Lastly is the Mackey-Glass time series dataset. You can take a look at the differential equation used to generate the data points. The table summarizes the results for timestamps 1 and 85 ahead. As before, the DNN FES model performs the best compared to any other existing model. We now demonstrate the use of DNN FES in the stock market prediction. For the stock indexes, we have used three primarily: S&P 500, DJIA, and HSI. For training, we have used the years from 2006 to 2011, and for testing, 2012 to 2021. The S&P 500 and DJIA have gentle swings. It is interesting to note that the testing captures the stock market crash that appeared in 2020. This is the year when the COVID-19 pandemic struck globally. Our hope is that the similar crash that happened in the year 2009 can help the model predict the crash in the testing dataset. The HSI index is different from the other two. It contains of much noisier fluctuations. Interestingly, the noise of the data masks any significant impact that happened due to COVID. The choice of the two types of stock is primarily done to demonstrate the effectiveness of the DNN FES model to predict both types of the stock's fluctuations. For pre-processing, the first step is price normalization. We take a 14 days window period and take the closing price 14 days before. We then normalize the current price with it. The next is the velocity, which captures the change in the normalization value, momentum, which captures the change in the velocity. As an input to the model, we also take the volume index of the stocks. The predicted value is calculated using the equation shown on the bottom right. This is how the signal looks after the pre-processing. The table summarizes the performance of the model from 1 to 7 days ahead. The graphs on the right shows the prediction of the testing dataset of 7 days ahead. The focus is also done on the COVID-19 stock market crash. The model is able to provide high correlation despite there being a small lag in the forecasted values. However, the lag is low compared to the other models such as SVM. We also compare the performance of FE-RNN, which is the work done by the previous year FYP student, James. We have replicated the exact same experiment setup with the only change of using Fole. On an average, there is a reduction of 23.45% of RMSE in S&P 500, 29.27% in HSI, and 27% in DJIA. In terms of R-score as well, there is an increase by 0.1 for S&P 500, 0.9 for HSI, and 0.23 for DJIA. We conclude by stating the limitation and the summary of the research work. The falsification method used needs to have the center of area as the defalsification algorithm. This is primarily because the fold requires the parameters that are differentiable in nature. The cross-entropy loss that is used is primarily developed for probability distribution. Fuzzy theory deals with possibility distribution. Despite having a subtle difference in the two, more work can be done on exploring other losses. To summarize, we have developed a novel architecture called DNN FES with a unique learning mechanism called Fole. The DNN FES model performs better, or at least is at par with the current state-of-the-art models under any dataset. For incorporates both the accuracy loss as well as the interpretability loss of the model. We also demonstrated the real-world application of DNN FES, taking the example of stock market prediction. Thank you very much for your time. Hope you liked our presentation.